All right. Thank you, everybody, for being here. My name is Christopher Patton, and I'm going to present some work I did with my advisor on the TLS 1.3 record layer. So first of all, that was the perfect talk to lead into what I'm going to talk about now, so thanks, and that was also really cool. Okay, so I guess I don't need to say this now, but if you missed it, for those of you who don't know, the record layer refers to the part of TLS that provides privacy and integrity of the messages sent in the protocol using the key negotiated by the client and server. And as the title of my talk suggests, our goal for this work was to prove security of the TLS 1.3 record layer as it is specified and without ignoring any specification details. You're probably wondering what this means, so I'm going to get right into it. So those familiar with the provable security methodology will recognize these 4 steps that are involved in analyzing real-world crypto systems. So you start with syntax, mathematically formulating what's the protocol or primitive that's under attack, and then you define what it means for that thing to be secure, who's the adversary, and what's their goal. And then you define what it means, and then you specify the system you're analyzing as an instance of the thing for which you define security. And once you've done these 3 steps, you're ready to provide a proof. But as we all know, and as we've just seen, attacks happen despite the existence of proofs. And when they happen, there's a few places to look for an explanation. But the most likely culprit is that there's something wrong with the model that you started with. Either the attack is out of scope of the adversary you had envisioned, or your syntax was incorrect. Perhaps you missed some important side channel that's available to the adversary in practice. And I say this is the most likely culprit because every model is wrong. Every model is necessarily limited in what it can say about real systems in operation. So what do you do when the model's wrong? You update it. And this leads to what De Gabriel et al. Have called the model attack remodel cycle. So first, a protocol is proven secure in some particular model. Then someone finds an attack. And then the model's updated. The protocol's patched, and a new proof is found. And it might be the case that the new protocol is less efficient, or the new proof has weaker security bounds, or requires stronger assumptions. But it's always the case that the new model now encompasses more implementation details about the system. And one consequence is that as the model gets more sophisticated, attacks become more detail-oriented, again, as we just saw. And this is because a good hacker is someone who's able to exploit details of a system that are outside the mental model of a system's designer. So, and the same is true, of course, for crypto systems. Rather than break the crypto directly, attacks often exploit features of real systems that are beyond the realm of expertise of the prover. And this means that attacks are difficult to foresee, and it seems like the best we can do is just react to them when they happen. And this also seems inevitable. We see the same game being played out in other fields, not just security. And it's also not such a bad thing because everyone here is employed because of bugs in programs. So let's see how this cycle has driven the evolution of our model for secure channel protocols like TLS. And my starting point is a paper from 2000 from Bellari and Nampompré, who looked at ways to build authenticated encryption schemes via the composition of a probabilistic encryption scheme and a message authentication code, such as HMAC. But today we've become more familiar with dedicated primitives for authenticated encryption with associated data, such as AES-GCM, which we're going to learn a little bit about later on. Very quickly, though, AEAD schemes are designed to provide privacy and integrity for the input message, but they also provide integrity for some associated data. Encryption is deterministic rather than probabilistic, and it takes as input a nonce, which in the security game we're going to assume never repeats. But AEAD schemes don't suffice for privacy and integrity of secure channels, because, at least on their own, because they don't prevent many attacks that secure channels are designed to prevent. So for example, if the sender and receiver are stateless, as they are in the security model for AEAD schemes, then it's impossible to prevent things like replay attacks. To do so, protocols like SSH and TLS use a sequence number that's incremented with each new message. So in their 2004 analysis of SSH, Bellari et al. Incorporated state into the model for authenticated encryption. But as you can imagine at this point, their model doesn't encompass all possible attack vectors. An important one, which we just heard a lot about, is decryption leakage. And a prominent example of an attack that exploits decryption leakage are padding oracle attacks. And I don't need to say anything more about that. But a lesser known attack, but to me I think is equally interesting, is the plaintext recovery attack on SSH described by Albrecht et al. In 2009. And unfortunately, I can't give you the details here, but this attack exploited the fact that SSH implementations are capable of processing ciphertexts as fragments rather than all at once. So in response to this attack in 2012, Boldireva et al. Extended the model of Bellari et al. By incorporating ciphertext fragmentation. And this new model essentially treats the ciphertext as a stream of bits, rather than as an atomic message that's processed all at once. And this more accurately captures implementation details of not only SSH, but any secure channel protocol in which the length of each ciphertext is conveyed to the receiver in band. And this includes TLS. In fact, secure channel implementations don't just treat the ciphertext as a stream. They also treat the plaintext as a stream as well. So in 2015, Fischlin et al. Incorporated plaintext fragmentation into the model, and this accounts for additional attacks on integrity that hadn't been considered by Boldireva et al. Okay. Oh, and so this is our starting point for our analysis of TLS. The takeaway here is that the more sophisticated the model gets, the more accurately it reflects the real system. And so the more implementation details matter for security. So the challenge for us is to figure out which parts of TLS are relevant to this in the security model and which aren't. But this might be trickier than you think. If you've read the TLS standard, well, no one's read the whole thing, right? You'll notice that every interaction between the client and server is completely specified. It's more accurate to think of the standard as a set of rules which must be followed, and then another set of guidelines which should or may be followed. This is because TLS needs to be very flexible. Implementations have varying security goals and make different performance trade-offs, and they all need to be interoperable with other protocols, as well as provide secure backwards fallback to prior versions of TLS. And there's also deployment considerations. For example, what does the underlying network do with the connection state? And there's also just a bunch of implementation details that are relevant to this model, which are not addressed at all in the spec. And I'm going to get into a couple of these in a little bit. But all of this means that standards are only partly prescriptive, and they provide rules and guidelines for fully realized implementations. And this is pretty different from what you might think if you've never read an RFC, that TLS specifies a collection of implementations rather than a single one. And as I've said, this is important for practice, but it also makes being proactive about provable security difficult, as it's hard to anticipate where vulnerabilities might arise in implementations. So we address this challenge by applying the partially specified protocol framework introduced by Rogaway and Steggers in their paper from 2009. And their idea is simple: to formalize what a standard actually provides, a partial specification of a protocol. So in this model, we'll specify only the aspects of the protocol that are essential to security, and we'll leave everything else unspecified. And what we want to be able to formalize is the idea that no matter how the unspecified part is implemented, security still holds. So I'm going to get into what this means and how we do this in a moment, but at this point I need to define our syntax and security goals for secure channels. In the stream-based channel setting of Fischlin et al., both the plaintext and ciphertext are delivered as streams of fragments. So note that there's not necessarily a one-to-one correspondence between inputs and outputs. Both the sender and receiver may buffer their inputs and output them in any fragmentation pattern that they wish. And this accurately models the myriad ways that implementations of secure channels may operate in practice. So our syntax extends this more or less directly in order to permit the analysis of TLS. So specifically, the record layer actually multiplexes a number of data streams over the same channel, each pertaining to a different higher level protocol. And those familiar with the spec know that these are the handshake protocol, application data protocol, and alert protocols. And we handle this syntactically by associating a value called the stream context to each plaintext. And this essentially models the role of the content type in the record layer. In our security games, the adversary can send arbitrary fragments to the sender and receiver and observe the outputs. And our privacy game is analogous to INDCCA in that the adversary sends a pair of fragments to the sender and is asked to distinguish which of the fragments gets processed. And as usual, we need to prevent the adversary from decrypting ciphertexts that depend on the challenge bit. And actually, this is somewhat tricky in the stream-based channel setting because, as I said, there's no longer a one-to-one correspondence between inputs and outputs of either the sender or receiver. It requires carefully defining what it means for the channel to be in sync. And I'm going to go through this really quickly. So in the game, we keep track of the ciphertext stream produced by the sender so far. We also keep track of how much of the ciphertext stream has been consumed by the receiver so far. Once fragments are delivered, they're buffered by the receiver and then consumed only when an entire ciphertext or sequence of ciphertexts is ready to be processed. So the channel is said to be in sync as long as the stream consumed so far is a prefix of the stream produced so far. And to prevent trivial attacks, it suffices to suppress the plaintext output by the receiver whenever the channel is in sync. And this basically follows prior work, and it formalizes the idea that you shouldn't be able to decrypt a ciphertext that you got from the encryption oracle. Okay, so we also define integrity of the ciphertext stream. Security in this setting means essentially that an efficient adversary can't cause the receiver to output any plaintext fragment whenever the channel is out of sync. And then plaintext stream integrity, on the other hand, captures the goal that each plaintext stream should be delivered correctly regardless of whether the channel is in sync or not. Okay. So to formalize the idea that the channel may only be partially specified, we provide each algorithm access to a specification details oracle, or SD oracle. So a partially specified channel, or PSC, is comprised of algorithms that specify part of the computation, and everything else we're going to leave to this oracle, the SD oracle. In our security games, we let the adversary answer the SD queries itself. So in our games, the adversary makes queries to its game oracles, which in turn invoke the PSC algorithms basically as usual, but not unusual. The PSC algorithms will in turn invoke the adversary for answering SD queries. So in our setting, the adversary effectively participates in the evaluation of its own queries. And this is clearly a very strong attack model, and we'll need to restrict the role of the SD oracle in some way. But a proof of security in this setting implies that the channel is secure no matter how the specification details are implemented. And this allows us to essentially ignore the specification details in the analysis. And one rule of thumb for doing this kind of analysis is the more you're able to push into the SD oracle, the simpler the analysis becomes. So in the remainder, I'll discuss how we model the record layer as a partially specified channel, and I'll begin by highlighting two particularly sticky points in the specification. The first is the relationship between the content type and the record header. And as I mentioned, the record layer has three content types: handshake, application data, and alert. And each record pertains to a single content type. And otherwise, there's a complex set of rules that dictate how to coalesce fragments into records, the length of each record, and the order in which records are output. And this is an area where the standard provides lots and lots of flexibility, but still every implementation must adhere to a core set of rules. The content type is encrypted along with the plaintext fragment. And this permits implementations that hide the content type so that the content type of a ciphertext fragment is indistinguishable. But the spec also permits implementations that leak the content type altogether. So for example, the length of each record might leak whether the message is an alert. And by the way, you're not meant to read that whole paragraph. I just wanted to put up some of the spec on the slide. So the point here is that the level of privacy that the record layer will achieve hinges upon details that are not fully addressed in the standard. The other sticky point is the record header. The record header is the sequence of 5 bytes that indicates, among other things, indicates the total length of the next encrypted record. And this is supposed to tell the receiver how many bytes it's to expect before decrypting. So when we began looking at TLS 1.3, it was still an internet draft, and at that time, the header was unauthenticated, and the receiver wasn't required to enforce the value of the header. And the reason for this is that the header doesn't seem to be relevant to security of the record's contents. But in order to achieve our strong notion of ciphertext integrity, all bits output by the sender need to be authenticated. As a result, TLS 1.3 prior to draft 25 isn't secure in our model. But this is somewhat counterintuitive, I think, because since the structure of the record header, and in fact, the manner in which ciphertexts are delimited in the stream should be irrelevant to security. And in fact, what we show in our paper is that these details are irrelevant to security as long as the header is authenticated. And so formally, what we do is we let the record header be chosen by the specification details oracle. So the change to the protocol that we suggested, and which was adopted in draft 25, was simply to treat the record header as associated data when encrypting. And with this minor change, we can define the record layer as the composition of 3 simple components. The first is an AEAD scheme that's defined as usual. And the second is a scheme for generating nonces. TLS uses a sequence number XORed with an IV that's derived from the shared secret key. And we're going to learn about why that's done in the next talk. So, and the third thing is what I call the stream multiplexer. And this captures the non-cryptographic operations that are involved in coalescing fragments into records, encoding records, and enforcing record boundary rules. The stream multiplexer also determines what level of privacy the record layer will ultimately achieve, whether it hides the content type and the lengths of fragments, etc. So as I said, it doesn't do any crypto, so we're not going to make any computational assumptions about this thing, but we do need to give sufficient conditions on this stream multiplexer under which we can prove security of the composition. And that's why it's important to pull this piece out as an explicit part of the construction. Otherwise, though, we're able to model everything else in the protocol as specification details. And this is really nice because it makes the record layer much simpler to analyze. And I'm mostly going to refer you to our paper to convince you of that, because it's simpler, but it's still not simple. So we prove this composition meets our notion of privacy for multiplex stream-based channels. And this has a few steps to it. First, we show that it meets a privacy notion that's analogous to INDCPA, in that we only give the adversary access to a sender oracle and not a receiver oracle. We then prove ciphertext stream integrity, as well as an additional property that captures essentially that decryption leakage should be efficiently simulatable. And finally, we prove that these conditions suffice for our target privacy notion. We also prove plaintext stream integrity, though our result has an important and I think interesting caveat. So the conventional wisdom for authenticated encryption, which was first observed by Bellari and Nampempre, is that ciphertext integrity implies plaintext integrity. And this result nicely matches our intuition, because if a ciphertext was produced honestly, then we'd expect it to decrypt to the correct or intended plaintext. As a result, though, the proof that ciphertext integrity implies plaintext integrity uses the correctness condition on the AED scheme in a very crucial way. But in our setting, the channel may only be partially specified, and as I've said, our goal is to prove security even if the specification details aren't realized properly. So we don't define correctness, and we don't assume it in our proofs. In fact, it's unclear how to define correctness without making restrictions on the SD oracle. Nevertheless, in the full version of our paper, we give a sufficient correctness condition, which restricts the SD oracle, under which ciphertext stream integrity implies plaintext stream integrity. But this is less general than we'd like, since it restricts the SD oracle and therefore the adversary. Despite this limitation, though, our results are largely good news for TLS. We've shown that not only a particular realization of the record layer, but all compliant implementations are secure with respect to our security notions. And these aren't the strongest possible, but they do capture lots and lots of details of real implementations. And of course, the PSC framework is not the only way to reason about unspecified behavior in TLS, but it gives you a way to think rigorously about what parts of the standard are essential to security and which aren't. And this provides guidance for determining which implementation details need to be explicitly modeled. And this is why I think the definitional perspective we adopt in our paper will make provable security more proactive. So where do we go from here? I think first, our framework can be applied more or less directly to other specifications such as SSH, IPsec, and QUIC. And we'd also like to see the partially specified protocol framework applied more broadly. So for example, to the TLS handshake. Thank you everybody for your attention.